So folks, we had talked about what your ear does in terms of hearing and the structures of your ear involved with that. Now we're going to focus on the other thing your ear does. And like he mentioned in the video, probably the more important thing that your ear does. You could get by without hearing, like you could get by with your day-to-day life, but without balance, boy, it's tough. In terms of balance, this is the basics. So just like I did with hearing, I'm just giving you a brief little introduction to it. You have mechanoreceptors in your inner ear that detect head movement. This is different than the mechanoreceptors that detect sound waves, moving fluid, although you'll see they actually work in a very similar fashion. The hair cells will bend, but this time they're going to bend not because sound made fluid move, but because physical movement of your head made fluid move. This initiates depolarization, so we're always bringing it back to the way neurons work. We send a nerve impulse to the brainstem via the vestibular nerve, and if you'll recall in the picture of the ear, there was the auditory nerve and the vestibular nerve and the facial nerve, which we aren't going to talk about, but that's the other nerve that was on the picture. So that's the basics of balance, but even within balance, there are sort of two sides to the story, and I want to show you those. The first thing that has to do with balance are the semicircular canals. So if you take a look here, the semicircular canals are those three long, tubey-shaped structures. They're on three different planes, kind of if you imagine up, down, left, right, and sort of the back, front. So on three different dimensions. The semicircular canals contain mechanoreceptors that detect head and body rotation. So think spinning, turning, twirling. I always think about figure skaters and those awesome spins that they do when I'm talking about this one. I tried to teach myself how to do that. A, I don't have figure skates, so it was kind of hard. And B, I can't. I just can't do it. Anyone here a dancer or skater and can do, yeah, Brielle, you can probably do like a bunch of spins in a row and not get dizzy. It takes quite a bit of practice because you have to teach your mechanoreceptors, or you have to do something with your head so that they're not being constantly activated. Otherwise, you're going to get this crazy feeling of being dizzy. The type of equilibrium or balance that we're talking about here is dynamic equilibrium. That's the term. When your head is twirling and whirling. Another time that you might think about the semicircular canals is if you're on some sort of amusement park ride. I don't go on those. They're too high, and I'm afraid of heights, you might recall. I can't do it. And I don't like it. I've been on them, and every time I go on one, I'm like, why did I do this? But roller coasters and that kind of thing would be really activating these mechanoreceptors. So these three loops, the semicircular canals, are filled with liquid, and they're arranged on three separate planes, like I said, one loop per spatial dimension. At the base of each loop, so right at the bottom, you can see we've kind of cut it open there, is this cup, this gelatinous body at the very base of it. And when the head turns, the liquid in the channels causes the stereocilia to flex. So if I zoom in on the base of one of these channels, this is what it looks like. At the base of each channel, you've got a branch of the vestibular nerve, some cells, the hair cells, and then the cilia sticking out. So like I was saying, it's very similar to the way the hair cells work in the cochlea, where the hair cells bend. Of course, things are attached a little bit differently. There's no basilar membrane and tectorial membrane through which the vibrations pass. But we still have little hair cells. They still have stereocilia, and the cilia are still going to bend, and that's what causes depolarization to happen. So same type of process, just slightly different setup for the hair cells. Now, if you have questions about semicircular canals or the hair cells within them, do you want to ask? Now, serious question. Does anyone love going on roller coasters? There's roller coaster junkies in here. Look at, you're all crazy. I don't know how you do it. Even if psychologically I told myself that I was going to do it, physically I can't. I get on the ride and I can feel like my stomach drops. I feel like I'm going to vomit. Even though in my head I know that it's probably safe and it's probably fine, I don't even like watching my kid go on them because I get the same weird nervous feeling.
That's the best part.
I don't like it. Don't like it. And it's funny because lots of things don't creep me out or gross me out, but being up high and falling, not cool. Can't do it. Okay. So that's one aspect of balance. The other aspect of balance has to do with this other part in your inner ear. It's called the utricle and the saccule, and they're part of the vestibule. So I'm just going to actually back up to the previous slide. Here's the vestibule right here. It's the base of where the semicircular canals are attached. So they're physically right next to each other. So the semicircular canals loop up, and the base of them is this vestibule that we're talking about. Now what's really important is that the vestibule, like most of your inner ear, is filled with this liquid, this fluid. But it's also got these little rock-like structures called otoliths, which I'll talk about in a second. You have another type of equilibrium called static equilibrium. This is the equilibrium that's determined by the tilt of your head. So not whether your head is spinning and moving, but is your head perpendicular? Is it bending forward? Is it leaning back? Just tilt of your head. Now, most movements that you do will impact your dynamic and your static equilibrium at the same time. But I think you could see how this particular one could be activated without actually turning your head. All you need to do is look down, okay? So if you look at a spot on the wall and then tilt your head forward to look down, you are activating this part of your inner ear. Now, these parts in your inner ear contain granules of calcium carbonate. Those are the otoliths. So they're blue here. I'm not sure why. They're not blue in real life. Most substances are white or beige in real life. That's just for fun. But these little otoliths, these little solid pieces of calcium carbonate, they're almost like little rocks. They're attracted by gravity when the head is tilted. So imagine you've got a bunch of little rocks in your ear, and you tilt forward. What happens? They slide forward. When you tilt back, they slide back. And so when you tilt your head forward, these little otoliths move. And when they move, they help push that liquidy, gelatinous fluid, and what's behind it? Hair cells. Just like with the semicircular canals or inside of the cochlea, hair cells with cilia. When the cilia on the hair cells bend, that's what causes depolarization. So if I think about how I hear and how I stay in balance, the answer is always hair cells. Hair cells bend. The cilia on the hair cells bend, sends an action potential. What exact scenario caused it to bend is slightly different, but it's a very similar process. They're all mechanoreceptors, so they're all responding to the physical movement of a fluid or a fluid plus some little solid rock-like structures that are causing the cilia to bend. Now, if you would like to ask a question here, I would love to answer it. Okay. So